Well, while we're waiting, I'll talk about what I've been working on today. So this is the kind of stuff I design. I developed a process, I think I've said before, for embedding ferrites into printed circuit boards. So this circle here, you can't really see. This would be a transformer, a ferrite core. And then it's like a toroid or like a donut. And so this one here is for the isolation transformer. And then this is a common mode filter. So this filters out common mode signals. So what this would be used for is for a battery management system. So they have on these battery arrays in automotives and things like that, they have a number of they segment the arrays in like groups of, let's say 8 or 12 or whatever. And then they have ICs that monitor every battery, and it monitors the state of the charge, how much charge is on the battery, and you know, how its temperature and things of that nature, how it recharges, how fast it recharges, and things like that. And then it also equalizes the batteries. Like if all the batteries, like if some are at 3.7 volts and then some are at 3.5 volts, the systems will equalize and share charge between the batteries to get them all at the same voltage. But anyway, they need a data communication channel to interface the battery. And so this is a transformer that isolates, like the control circuitry on the data communication channel is like at 15 volts. And the battery that it's going to interface, let's say this is the control interface where the microcontroller is monitoring the batteries.
Oh, they left. My ponies left.
Over here, you know, it may be as much as 1200 volts or 2000 volts. So what this transformer has to do is it has to, you know, pass like data at like 4 megahertz data rates, nothing really fast. But it also has to provide like 5000 volts of voltage isolation. Between the blue and the green are the secondary windings, and then the red and the yellow are the primary windings. So this is like a transformer that's embedded in a printed circuit board. And the thing about it is printed circuit boards are very good insulators, the materials. So it provides very good isolation. So I'm working on this for a customer today. I've got a number of variations. Everybody wants them slightly different, but I've been spending a lot of time on these data channel isolation transformers lately. Okay, so but anyway, back to our lab. I think I'll start here. Let me just go through this real quick and see who else needs to be added to record. Well, it looks like we only have 8 today. It's 6:07, so I'm going to start. Okay, so we're going to do MOS devices today. The way we're going to be working with is an NMOS device. And these are just some pictures I pulled off the web that are pretty good representations of how these work. So you've got what we call a source and a drain and a gate. And frankly, I don't think in a lot of these devices it makes a difference whether you hook the drain up here and the source here, because they're pretty much symmetrical. But anyway, for an NMOS, you'll have like a material with P, and I think that means it's doped with boron. And then you'll dope wells in that P substrate with phosphate to create N-type material. And then they've got a, this is the bulk silicon connection, and this I guess has extra P doping here. So they'll get a silicon wafer excuse me, that's first started with a boron doping. And then maybe during the process, they'll put a little bit extra. And frankly, I'm not sure why they have that extra well, or I mean, why they would have to dope that extra. I don't know, maybe it has something to do with the electrical contact. So that's a NMOS, and then PMOS, you'll start with a P substrate, dope a N well, and then dope P in it. So it takes a little bit more processing to create PMOS. But then this is basically what the gates look like. You'll have metallization on top of the silicon for the drain and the source, and then you'll have the gate. And so the gate dimensions is really kind of defines a lot of the performance, as we'll see in a moment. But basically, you've got this piece of silicon with this piece of metal on top of it. And it's got these free electrons in there. And so when you put a field, or when you put a voltage here, it creates a electromagnetic field that attracts the electrons to it. And that basically creates a channel for conduction between the source and the drain. And that's basically how they work. They're actually rather simple. We'll be doing bipolar later. Bipolar is still useful for a lot of instrumentation, and then it's used in a lot of power electronics, bipolar transistors. But today, a lot of the microprocessors are basically based on CMOS and metal oxide semiconductors, and they're basically FETs that create, or those devices are basically FET technology. Okay, so now just going into the pre-lab. So here's the model, the schematic model of the device. And so we have the drain, the source, and then between the drain and the gate, we have VGD and VGS. And so and then this one, for the NMOS, it shows the arrow pointing in towards the bulk silicon. So our first question in the pre-lab is, it says VDS is greater than VGS minus VTH. So let me actually get the instructions and read what it actually says. It says, one of the conditions for forward active saturation region operation is that VDS is greater than VGS minus VTH. Show that the condition is equivalent to VGD is less than VTH. And it says, what other condition, excuse me, I'm about to sneeze. What other condition, what is the other condition for forward active operation? Okay, so we have VDS. So VDS again is VGS plus VGD. So if we look at this, here's the drain and source. So the voltage between the drain and source is essentially the voltage between the drain and the gate and the source. So we can rewrite this as VDS is equal to VGS plus VGD, which is greater than VGS minus VTH. And then we can basically, because we got VGS on both sides, we can basically remove it. So we end up with VGD is greater than minus VTH. And then in the pre-lab, it says, show that VGD is less than VTH. So if we multiply by -1, that basically flips the sign, and that -1 goes away there. So it basically becomes VGD is less than VTH. I think I said that right. Yeah. And then the other condition is that when VGS is greater than the threshold voltage, VTH, the FET transistor will be in the forward active region. So, oh, it looks like we have some new participants. Let me go in here and see if we can get them recording. Who else joined that I didn't allow to record? Okay. Okay, if I haven't allowed you to record, speak up. I think I got everything. Okay, so now the next thing here, this is just like a characteristics from a data sheet. And what this is showing you is what kind of current you'll get out of it with different voltages of across VGS. And then what we're going to be actually simulating is we'll do like the gate voltage versus the gate source voltage. I'm sorry, we'll do the drain voltage versus the gate source voltage, and we'll also do the gate current, the drain current versus the gate source voltage. But the point is, in the lab, it'll ask you to identify the different regions. And so before the FET turns on, when there's very low, there's no current really flowing through it. It's got very high resistance. It's basically like an open circuit. That we call the cutoff. And then there's like this transition region, which happens actually really quick over rather small voltage. You know, and what we'll see is it's probably like within 2 volts or something. But that we call the forward active or triode region. And then when it levels off, we call that the saturation. So we'll see that in our simulation. But anyway, in our report too, it'll ask you often to label in the lab write-up, it'll ask you label the cutoff, the forward active, and the saturation region. So you'll want to annotate your graphs with that. Okay, so now step 2, it says for the circuit in figure 1, we'll take a quick look at that. Figure 1. Here's our transistor. So we basically have a resistor, and we can control the current going through the FET. The source is connected to ground. The drain is connected to the resistor and VDD. And then here's the gate. And this is something that I don't know. I had a question in my class yesterday, and I don't know the answer to this. This is just like the convention. But, you know, intuitively, you would say this is the source where this current comes in, and this is the drain where it comes out. But in any event, the convention that we use is that this is the drain here, and then this is the source. So that's a little confused. It's kind of counterintuitive. Okay, but anyway, going back into my my preliminary calculations, we have to set this up. We've got the supply voltage minus the the drain to source voltage. If I look at that schematic one more time, let me see. That is over. I got too many windows. Okay, so the drain to source voltage is equal to supply voltage minus the current flowing through the resistor and the resistor times the resistor. So there's a voltage drop here. So to set up that equation, to find the drain to source voltage, we have VDS is equal to VDD, the supply voltage, minus ID times RD, which is VDD. And then there's an equation we have in the pre-lab here. I've basically have reduced it down. The equation for the current going through the FET is ID is equal to K, and K has a value. K is like a representation of a bigger value. If you look at the write-up, it has micro C oxide, so the capacitance of the oxide, times the width divided by the length divided by 2. So you'll see that referred to a lot of times in the lab. We're going to just treat that as a constant in most instances. And so we'll just assign that the value K. So this micro COX W divided by L divided by 2, we'll call that K. And then it's equal to K times the gate source voltage minus the threshold voltage squared. So we have VDD equals 5 volts and the resistance is 4.7 K. And then for the FETs that we're using in our lab, we're going to be using a data sheet or we're going to be using Appendix 12. So this is on Moodle. If you scroll down to the bottom of the Moodle page, there's an Appendix 12.1. And so this is the device we're actually going to be building with. This is the CD4007. And to build the model for it, we don't necessarily have this model in PSpice, so we're going to have to build it. But what we're going to do is we're going to copy these devices and then paste it into a generic model. And I'll show you how to do that in a bit after we get through the pre-lab. But whoever's gonna, I think, was it Alex or who told? Oh, Shah, Amir, you said you were gonna run the PSpice today. While you're at it, see if you can find 12.1 in the Moodle page, my Moodle page, and then go to the bottom, and we're going to want to copy this first top for the NMOS. The bottom
Okay.
half is going to be the PMOS. Okay, so anyway, though, back to our pre-lab. If we look at that model, I'm jumping back and forth quite a bit here. Let me go back to that model. Where was it? So in this one, it says that our voltage threshold is 1.6 volts, and then our Kp constant is 0.000820. And then it says the width of the gate is 15 microns and the length is 5 microns. And then phi, I forget what phi and gamma. This is the oxide thickness, I guess, which is 1200 nano. So a lot of these things we're not going to use, but we are going to use this Kp factor and this threshold voltage in our calculation. So now back to the calculation. So we have VTH equals 1.6 volts, K equals 8.2. So we have the equation that ID is equal to 8.2 times 10 to the minus fourth times VGS minus VTH, which is 1.6 squared. So our equation looks like this. And so what you're going to do in your pre-lab is you're going to put in, calculate the value for ID and put that here. And then you're going to calculate the value for VDS, the drain source voltage, and put that in here. And you're going to use those equations. And then when VGS is 1 volt, so that's below the threshold of 1.6, we're in cutoff. So that the FET is not conducting. And then when it's 2 volts, that's going to be in the forward active region. And then by the time we get to 4 volts, it's going to be in saturation. So that's the equation set up. You can do those calculations, including your report. And then step 3, it says, suppose that an N-channel MOSFET, and it says not the CD4007 type. So it's just like a generic N-channel MOSFET, is measured to have an ID of 35 microamps when VGS is 1.46 volts, and an ID equal to 430 microamps when VGS equals 2.18 volts. Solve for VTH rather, and then the K factor, which again is the micro COX divided by 2 times W divided by L. So what we want to do, we've got the current and we got the VGS. So we basically want to set up 2 equations and 2 unknowns. And so we have this equation here again. And so we'll set it up. 35 microamps is equal to K times 1.46 volts minus VTH. And then 430 microamps is equal to K times 2.18 minus VTH. So we got 2 equations, 2 unknowns. So you'll have to do some algebra there and then calculate it. And in the pre-lab, it says, okay, VTH should be 1. You should get 1.17 volts for VTH. And then for the K factor, you should get 4.23 times 10 to the minus fourth. So it actually tells you the answers there. But we'll need to do that same calculation for I think it's step 9. Yeah, step 9, we're going to have to do that same calculation. And then for the build portion of this lab, we'll use the parts out of the analog discovery kit. So there's a ZVN3310 N-channel MOSFET, DMOSFET, and YOU. In step 11, we bias the bulk silicon to a different voltage. We'll skip that. We don't have that capability. And so there actually is going to be somewhat of a disconnect, because in the PSpice, we're going to model with the CD4007, which is what the lab was originally designed around. And then for these, since we started doing these over Zoom with the analog discovery, we're actually building with this device here. So we're not necessarily going to get a matchup of performance in Spice to the actual performance we test in the lab. But nevertheless, I mean, we'll get some experience doing simulations and building and so forth. Okay, so at this point, we're going to go off and build this circuit and simulate it. So I'm going to hand this over. I'm going to stop sharing and I'm going to hand this over to Amir. And Amir is going to open up PSpice and do the simulation for us. Okay, good. Okay, so the first thing we'll do is we'll go get our FET. So we're going to do is we're going to use a generic model. So they has generic models for MOSFETs and transistors and diodes. The one for the MOSFET is called mBreak N4. So why don't you just type that in, see if it shows up. If not, we'll have to go search for it. mBreak, oh, there it is. Yeah, mBreak N4, good. So let's bring that.
Is this one?
Yes, yes. Let's bring that in. Okay, good. Okay, so now it's just a generic model. So if you click on it and it turns pink, okay. Oh, let's go back to the schematic. Okay, now let's right click on that. And you see where it says edit PSpice model about, yeah, a little bit lower, edit PSpice there. Yeah, that one. Let's click on that. And a window should pop up at the bottom of your screen. Okay, so now we got to go to that that appendix and copy the top half of those parameters and then paste them in there and then save it. Yeah, copy
So
that.
was it just this portion right here?
Even the top line as well.
Okay.
Yes, copy that. And then we'll go back and paste over that, paste over everything. Okay, and then do a file save. Yeah. Okay, now let's look at our schematic again. So now it's got the part number. So I think that worked out okay. So we've got our part number now. So now we need we need two supplies. We need one for the gate source. We need one for to power at the drain, and then we need a resistor. So we'll use VDC at the gate source. We'll use VDC. Yeah, let's bring in two of those. So put one on the left, put one on the right. Yeah, that's good. Good. And then we'll bring in a resistor. We'll make it vertical. Yeah, and let's put that up at the drain above the, yeah, that's a good spot there. Yeah, perfect. Okay, so let's wire this thing up. So we'll have a wire, yeah.
All right.
Okay, and that goes to the gate, good. And then that goes to the top of R1.
Oh, okay.
Yeah, and then everything else will go to ground. Yeah, good. And you always got to get below that little bubble. And that's the bulk silicon, just connected vertical. Yep, that's good. And later on, we're going to put a battery in there, but for now, that's good. Okay, so that's basically our circuit. So the source is connected directly to ground. Our resistor, let's make V1. Oh, okay, that's 4.7K. Good. And then V1, let's just make it 2 volts for now. Okay, and then that one will make 5. Okay, good. Okay, so that's basically our circuit. So the first thing we're going to do is a DC sweep. Let me read the SPICE simulation here again. Enter the circuit figure 1. Use the parts given in step for the MOSFET and appendix 12.1. Okay, so we don't have to specify the W and all that kind of stuff. Set VDD to 5 and sweep VGS from 0 to 5 volts. So that'll be supply number V1. From the simulation results, obtain a plot of ID as a function of VGS. And then also add a trace that is a mathematical expression. Okay, so first we'll just do that. So let's set it up to do a DC sweep. Hold on a second. Let me get this out of the way. Okay, so our DC sweep, the gate source is V1. So over to the right where it says name, we'll make V1. And then we'll go from 0 volts. Yeah, 0 to 5. And we can use 0.1 volt increments. Okay, and then we'll apply. Okay, good. And now we can just run it. And it should show up the bottom. Okay, that's all good. Okay, so traces. So the first thing we'll look at, so the bottom is VV1. So that's basically our VGS. So the first thing we'll do, we'll actually look at the current going through the drain. So you see the second, oh no, let's go back. Yeah, no, you're good. You're good. Go see where it says M1. So M1's our device. And then D is the current going through the drain. So let's click on that. And let's just take a look at that. Okay, so there's the current going through the MOSFET. So to the left, it turns on at 1.6 volts, right? That was in our model. And so to the left of that, we're in cutoff. And so again, in the lab, it says annotate this. So you want to put a vertical line in your report and say, okay, that's cut off. And then we got the transition there. That's a forward active. And you'll see it only goes from like 1.5 to 2.5. And then we're pretty much in saturation after that. So that's the forward active or triode. Yeah, and yeah, snip all that and open up a Word document and put it in. We'll take a moment. You can cut and paste your schematic.
So you said from 0 to 1.5, that's when it's
Cut off.
cut off. 1.5 to 2.5, that's when it's transition, and then
Yeah,
afterwards it's
technically it's 1.6. That's where the threshold is. Yeah, and then
Okay.
after that, where it levels off again, that's saturation. Okay, so did you have a chance to cut and paste your schematic in there too?
Oh yeah, I should do that too.
Yeah, if you want to put it in Word and type some notes, that's fine.
Mhm. Okay.
Okay, so let's go back to our plot again. Okay, so we'll see the current. The current's very low, right? It's yeah, you know, it's in saturation when you got like those are nanoamps, right? Are
Or
those-
milli.
yeah, there's not a lot of current going through there. But you know, you can drive those things with more. I think that's I'm seeing an N, or is that M?
That's M.
Milliamps? Okay.
Yeah.
Okay, so you can drive like 1 milliamp, but you can drive more current through it. But I mean, you're going to be, you know, as soon as you get to like 1 or 1.2, you're going to be in the saturation. And frankly, I mean, that's where a lot of these devices are used as. They're used as switches. And so they have fast transitions. And so like in digital logic, you're not really interested with the forward active or triode. You're just interested in the cutoff and then the saturation region, which would be a 1, and then the cutoff would be a 0. Okay, so that's the current. So let's go down and get rid of that. And let's just look at what's going on at the drain. So why don't you just click on that current down there again and just press on, no, go down to the, yeah, delete that out.
Oh
See
yeah.
if you can just delete it. Or yeah. I think if you just press the delete button, it will go. Okay, let's just look at the gate while we're at it. Trace, add trace. So now let's get rid of the current and the power. And I said the gate, I mean, let's look at the voltage at the drain. So let's look at the voltage and yeah, yeah, that one. Okay, so when the gate is below 1.6 volts, that FET is like an open circuit. So the drain is being pulled up to 5 volts. There's no current flowing through the FET. And then we get a 1.6 volts and it starts its transition. And then by the time we get to 2.5, it's pretty much being pulled to the ground. Here, it looks like it doesn't go absolutely to ground, but I mean, it's basically an inversion, right? So when the gate goes high, the drain goes low. And when the gate goes low, the drain goes high. So why don't you just capture that and we'll have that as the gate voltage.
You said something about it being an inversion.
Yeah, when the gate goes high, the drain goes low.
Mhm.
And when the gate goes low, the drain goes high.
All right, thank you. Okay.
Okay, you captured all that? Okay, so
Yeah.
let's get rid of that down at the bottom corner again. So this next part of step 4, it asks us to write an equation for basically the ID equals K VGS minus VTH. So we're actually just going to try to brute force and write an equation for this rather than just do it. So let's go to trace, add trace. Okay, so now we're going to put in our K value. So let's just type down there 0. Yeah, down there 0.000. And then what was it? 0008. Oh, I have it written down. I have it written down here. Where do I have it written down? Oh, I gotta go look again. Oh, I had it on my notes. Oh, actually, though, it's difficult for me to get to my notes. What was it? 00082. Oh, I think I have it written down in here. Yeah. It's 0.00082. Okay, so you got that. And let's put a little star times. Okay, and then we're going to scroll into the math function there and let's find power to the right. P. Yeah, that's the one. Yeah. Okay, so now we're going to go select V. Let me think. We want the gate voltage, or we actually want our voltage coming in. We want our voltage from V1. What was it? It was V1. Let's put in V1 plus. Yeah, right there. And then write minus 1.6. And then I think there's a comma there. We have to get on the other side, that 1.6 on the other side of that comma. That's why this is so difficult, because it's so tiny. So we
The
want,
comma's to the left of the 1.6. Do you want it to be on the right?
yeah, we want that. We want the comma on the right of the 1.6. Yes.
Okay,
want,
so right here.
yeah. So the equation is, again, it's VGS minus VTH. So we got our VGS, and then there's a plus in there. Is there a colon plus in there?
Yeah, colon plus.
Let's get rid of the colon plus and just have. Oh, wait. I'm confused. I'm sorry. This is tricky because it's so tiny and it's hard to read. Let's clear that out again and let's try that again. You can keep the 0082, but let's put in that power again. So what you're going to put in is the VGS. Yeah, that one. And then put in that one there. Yes. Do the 1 plus, V1 plus.
Oh, V1 plus. Okay.
And then put a minus. And then put 1.6. And then on the other side of that comma now put 2. So that's the square function in the power. Okay, let's see what we got. Let's press OK and see how it comes up. Okay, good. We got a parabola there. So that's the that's basically the equation for what's going on in the forward active region. So it turns on, like, again, around 1.6. So while we're at it, let's just overlap our ID again and see what that looks like. So let's go up to trace, add trace, and then current. Yeah. And let's go to M1D. Yeah, let's put that one on there.
Oh, M1D?
Yeah.
M1B. There we go.
Okay. So yeah, that's basically it kind of approximates. But see, what we're basically, what the point of this is that it's a parabolic function for the forward active. And so the parabola isn't showing us what's going on in cutoff or in saturation. But anyway, I mean, we grunted through it and we wrote the equation based on the ID equation. So let's capture this. That was basically the second half of part step 5, I think, step 4. That was the second half of step 4. Okay, and then it says, did you capture that?
Yes.
Okay, so I think we can clear all this out now. Okay, and then finally it says, add a plot showing VGS, VGD, and VTH. To plot VGD, you'll have to do a math function. We'll actually do VG as well. So let's go to voltage. Yeah, get rid of currents. Okay, so let's do M1D and M1G. Good. And let's just see what those look like. Okay, good. Okay, so it also wants VTH. So VTH is 1.6 volts. So we'll just go back there and add another trace. And we'll put in just 1.6. Okay, and then, oh yeah, just say okay. So we've added that to the mix. I'm not sure if that really tells us too much. But then finally now it says we want to put in VGD. And what we have to do for that is we'll basically take the drain voltage and subtract the gate voltage. So put in VD minus VG.
So like this?
Yeah, do you have a minus sign between those?
Yeah, right here.
Okay, let's see what it looks like. Okay, so that's basically it. Let's put our scale, let's go to the right and just do the scale from I'm sorry, the left. And let's do the scale from y-axis. Let's go from yeah, let's do user defined. Let's just go from 0 to 6. Okay. Okay, so that you see the red lines, your gate, the green one's your drain, the other one's VGD, and then the other one's your threshold. It is what it is. You know, Perry writes these lab reports and I execute them. I don't know if I know exactly what important information we're taking from this, but anyway, it is what it is. So we'll just capture that. That's the second half of step 4. So now we have step 5, and we're going to skip step 6 because it's not, there's a typo on the lab report. There is no step 6. And then we got step 7. Okay, so we're going to have to modify our circuit now for step number 5. Okay, so in step number 5, it says change the circuit by removing RD. So we're going to remove the 4.7K and we're going to have the wire go directly to V2. Okay, and then we're going to set VGS to 2 volts. You already have it there. And then what we're going to do this time is we're going to sweep V2. Okay, so when it's at 2 volts, we know it's going to be in the forward active range. Okay, so it says sweep VDD from 0 to 5, obtain a plot of ID. The transistor is in its linear region for low values of VDS. Identify the value of VDS at which the transistor transitions into saturation. Find an approximate value for the resistance, which is delta VDS over delta ID in each region. In the linear region, set one of the cursors to 0 and set the other to the low value. Compare the value of delta VDS over ID to RDS. So they have an equation there. You can do that analysis in your, you can do those calculations. Okay, so anyway, we're going to sweep V2. Yeah, it looks all good. So let's go ahead and just do that. Okay, trace, and we're gonna look at ID. We're gonna look at ID. Okay, so the forward active region is we're at 2 volts bias at the gate, and then we're sweeping the power supply. So the forward active region is that vertical at the left-hand side. And so at 0 volts, if we let's add a cursor there. Okay, so at 0 volts, we have 0 amps. And then if we go out to, let's go out to 0.2 volts. Let's put it, so yeah, right about there. So there we have 149 micro.
Yeah, micro.
Microamps, and we have 0.2 volts. So the resistance there is 0.2 divided by 149. Times 10 to the minus 6. So I get the resistance in my calculation, I have 0.2 volts divided by 149. I get that the resistance in that forward active is 1.342K. Okay, so then it also says to do it in the saturation region. I don't know if I really trust those values, but anyway, so do you want to capture that first and then just write the equation for your lab?
Yeah. Okay.
Okay, so if you want to type, you can type that delta V ds divided by delta ID is equal to 0.2 volts divided by, I think, 149 microamps. And when I punched that in, I got 1.342K. Okay, so that's the forward active region. Now it also says do it for the saturation. So it turns to saturation around 0.5 volts. Now this is rather tricky. I don't even know if I trust these values. So let's go from like 0.5 out to okay, here, I'll write the numbers down while you move the cursors. So when the cursor is at, let's actually just put it at 1. Let's put the cursor at 1 volt. Okay, so at 1 volt we have 196 micro, is that right?
198.67 micro.
Okay, I'll just say with 198.67 microamps, 1 volt. Okay, so let's move it out to I don't know, let's move it out to 5 volts and see what we got. Five volts, you got 206.
Yeah, 206.13 U.
Okay, so the delta there is, where'd that calculator go? Okay, 206 minus 198. 198. So we have 8 microamps, and then we have a difference of 4 volts. So we have 4 divided by 8 E6 minus gives me, it says, okay, basically that it's 500,000 ohms. Now that isn't intuitive to me. That bothers me because we're in the saturation region, and so it should be conducting, and I would expect that number to be much lower. But you know, it is what it is. I don't know if I fully understand that portion of the calculation. But anyway, for your notes, why don't you capture that, and then for your notes, you can just write, or you already captured it. For your notes, just write in the saturation region, we had delta VDS equals to 4 volts divided by 8 microamps, which is equal to 500,000 ohms. which again, I don't know if I really trust that, but hey, it is what it is. Okay, we're in the home stretch.
Is right here.
That's good. Okay, good. So finally, we got to put our resistor back in. Still 4.7K. Yeah, you can hook it up like that. Okay. And now we're going to add another battery. So we're going to put it just to the left. We're going to put it just to the left of that line that connects to the bulk silicon. So go down lower. Low, low, low. That's good. No, you had it. I'm sorry, left. I'm dyslexic, apparently. Put it to the right. The right side. There you go. Okay, perfect. Okay, so we're going to set that as -1 volt. So we're going to connect the bulk silicon to -1 volt. Okay, and then we're going to break that wire. Yes, that one there. Just cut that out and then connect the top to V3 and then the bottom to ground. And then we're going to run it the DC sweep again with V1 being the one that's going to be buried again. So we'll switch that around to where, yes. And yeah, just go ahead and run that. And we'll look at our display. Okay, so we tied the bulk silicon to -1 volt. Anybody got a guess what's going to happen? Let's do trace. Let's do the we can look at either ID or we can look at let's look at just we'll look at the drain. Yeah, look at the drain voltage. That's good. Oh, what's going on with our scale? Weird. Let's plot ID instead.
Yeah.
Okay. Okay. Oh, our scale got it looks compressed to me. Actually, let's adjust that scale. Let's adjust the I don't know what's odd to me is it looks like our transition, our forward active region stretched out. I expected to see the saturation. Let's see. Let's modify our simulation. Yeah, let's go modify our simulation profile. Let's run it out further. I mean, it's basically showing us the data. It just looks funny to me. Let's go from the end value. Let's make it 10 volts. Okay, let's do that again. See what that looks like.
You want to do ID or VD?
Let's do ID. Huh. I'm a little bit puzzled. Let's look at our schematic. Maybe I'm overlooking something. Oh, let's make that resistor 4.7K.
Oh, there it is.
That's what's puzzling me. Okay, let's try that again. Okay, so we don't have to run it all the way out. Let's go to the bottom and we'll just cut that. Yeah, click on that bottom and we'll go out to 5 volts. Yeah, there you go. Okay, so what happened? We tied our bulk silicon, our turn on, our threshold voltage was 1.6. And then when we tied the bulk silicon to -1 volt, it went out to 2.6. Okay, so it's switched. So that's kind of counterintuitive. You'd think, oh, geez, we tied it to -1 volt, you know, it might go the other way to go to like 0.6 from 1.6. But what happened is we, if you can imagine that field that we apply at the gate, before it was just going, it had to go over, the bulk silicon was at 0. Now we've got added another volt that it has to cross. That energy has to pull from, I don't know if I'm expressing this well, but basically we've increased the potential that the gate field has to pull from to bring electrons up to underneath that gate and produce conduction. I'm not sure if that was so articulate, but anyway, what we just learned is that when you connect the bulk silicon to a lower voltage, it pushes the threshold voltage up. Okay, that's basically our simulation. That was step 7. So next week, we're basically going to build these things, and we're going to basically be doing DC sweeps with them in the lab or with our analog discoveries. I don't think we send any small signals through them. Yeah, that's basically it for today. Yeah, Lonnie, class is done. So let's see, I'll look at the questions real quick. And let me move this out of the way. There's some more comments. Thanks, Amir, for running the show.
No problem.
Class is done. That's pretty sick. Tragic. 69.2 average and 130. I feel as though I have midterms every week. Yeah, I'm super burnt out right now. Funny. 3 midterms in 1 week. Oh, okay. So anyway, we are essentially done. Does anybody have any questions or any issues that we got to discuss? Okay.
I don't think so.
Okay, then I think we can end this. Thank you, everybody. We'll see you next week. We'll build it. Should go pretty fast because we're just going to be doing some little DC sweeps. Let's see, there's 7, 8, 9, 10. So there's 8, 9, 10, 11. There's 4 steps that we got to do next week. And it's all, I think, pretty much just little DC testing. Okay, have a good evening, everybody. Thank you.
Hey, Professor.